Well, thank you very much for having me here. I'm Lodovico Scarpa I'm working at the University of Oxford, where I'm just actually completed my PhD. And today I'm going to be talking about the emergence of irreversibility in isolated quantum systems. So I'm going to start by showing you two videos, and I'm going to ask you to guess whether I'm trying to trick you and showing the videos backwards, or whether I'm showing you the videos as they were taken. You can type in the chat if you like. So this is the first video. And this is the second video. So as you're probably all guessing, the first video was shown backwards in time, while the second video was shown forwards. And the reason that we can tell that is that in these videos, we're seeing some processes that we always see happening in one direction, and that we call irreversible because we see them happening only in this one direction. So in our everyday experience, we always see some system that starts from out of equilibrium. For instance, it could be like the tennis ball in the air. It could be a coffee getting cold in a room, going from this out of equilibrium situation and reaching an equilibrium state, for instance, the ball on the ground. But we never see the opposite process happening. The ball going, spontaneously, gaining energy from the ground and kind of starting bouncing back up and eventually ending up in, staying in the air, obviously. So there is this clear asymmetry here. Yet at the microscopic level, the quantum laws that govern the dynamics of atoms and electrons and other particles, and ultimately everything we know, they all happen, all allow processes in both directions. So if I can go from an initial state to a final state, then the reverse process must also be possible. So I must be able to go from the final state to the initial state. So there is no preferred direction at this kind of underlying microscopic level. There is no preferred direction for these processes. Yet in our everyday experience, we always see them happening in one direction only. And more than that, we know that these dynamics are recurrent, which means that whatever initial state we start with, if we just let the system evolve naturally under these microscopic quantum laws, then we're always going to return arbitrarily close to where we started. So why don't we observe these recurrences, and why don't we observe these processes happening in the reverse way? So one could start by saying, well, perhaps these quantum laws are actually incorrect. But in fact, one can do experiments and one can see these recurrences. Of course, we're talking about systems of few atoms, but they can be seen. One can see these microscopic dynamics, and we know that the laws, these laws have been tested up to incredibly high precision. And at the same time, if we look at systems made up of many atoms, but still not big enough to be macroscopic, not as many atoms as a chair, say, we do see that they naturally reach equilibrium. There are experiments that show this too. So in a sense, both views are correct. How do we solve this paradox? So one way that we could start thinking about it is that we could say, well, let's think of the drop of dye in the water that is spreading out in the glass. Well, there are a lot of more ways in which I can place the molecules of that dye or that ink throughout the water in the glass than if I put them all just in one corner. So kind of statistically, it seems more likely that the molecules are going to be spread out all over the glass rather than being concentrated in one corner. And that makes sense and it's intuitive. However, really here what I will try to cover in my talk is something more foundational, deeper than this. which is the dynamical point of view. So how, sure, we have this statistical argument, but what guarantees that the dynamics will bring us, will move the ink to this like kind of more statistically significant configurations? And what are the timescales? What are like the physical principles that lead to this evolution? So, so this is kind of like at a more foundational level than this statistics. So to start explaining like how this works and kind of resolve this paradox, we need to first talk about like divide this process in two parts, let's say. So the first one is equilibration. So this is just reaching an equilibrium state. So reaching a state, starting from some initial state, evolving in time, and then reaching a state of equilibrium. So a state that is constant in time. And then there's thermalization. Thermalization is a much stronger concept than equilibration. It requires equilibration to happen, but it's stronger than that because it also requires losing essentially all information about the initial state. So, for instance, think about a cup of coffee in a room. It's cooling down because the room is colder than the coffee, but it doesn't really matter whether the barista made the coffee a bit hotter or a bit less hot. At the end of the day, the final equilibrium state of the coffee will be like its temperature will be roughly the same as the temperature of the room. And similarly, in the example of the tennis ball, say, it doesn't really matter whether I make it start like from I make it fall from a bit higher or a bit lower. At the end of the day, like thermodynamically speaking, like the equilibrium state is just going to be the ball on the ground, and there's not really going to be a difference. So we need also, it's very important that we have also these forgetting the initial conditions. And so the first way to start like kind of solving this, the first point in starting to solve this paradox is to note that actually equilibration does not happen exactly. It's only kind of apparent, only effective. So if we look at some, let's say we have some quantity that we want to measure in the lab, and we look at it and we study its fluctuations around equilibrium as a function of time. So we start in this very big fluctuation that is the out of equilibrium state. And then we see that it kind of like goes down and starts having like only small fluctuations, and some are a little bit bigger. And eventually, as time goes forwards, and this might be in a very long time, but eventually as time goes forwards, we have a recurrence. So we return like to the, or very close to the equilibrium state, to the initial state, sorry. So, and in fact, we can see and one can show also that like these fluctuations are extremely small and extremely slow for the vast majority of times. So this is equilibrium in a sense, but it is only effective because in reality the state never stops changing. The dynamics never stop. You never reach a state that is truly static. And the mechanism. So one might wonder, well, why are we going, why do we have some fluctuations that sometimes are very high and actually the vast majority of times are very small? What is the mechanism that leads us to seeing this? Well, we can think about it in this way. Think of a high fluctuation as having kind of a lot of information. So initially we have these clocks. Let's think about it with this analogy. We have these clocks that all point at like the same time, same hour, same minute. So we're very certain of like what's the time. But now let's say these clocks have actually been made badly. They've been made and they're unsynchronized. They kind of tick in different ways. And now, as time goes forward, the hour, the hand of the hour stays the same, but the hand of the minutes starts getting kind of start being different between the clocks. So we start being more uncertain about the time. And as time goes forwards, now the clocks are giving us completely different times. And so we're very unsure about where we are, what time it is. And this kind of corresponds to the small fluctuations. But this might take very long if we have a lot of clocks, but actually, eventually, the clocks will all synchronize again. And that is what the recurrence is. So this was the equilibration part. So what about the thermalization part? So once we have reached this kind of state of effective equilibrium, how is it possible that we actually forget the initial conditions? Because the equilibrium state still has a lot of memory of the initial conditions, not all, but a lot. So how is it possible that we forget essentially all of it? Well, the answer is in essentially the measurements that we're able to make. So when we have this system of like many atoms, it can be like hundreds of thousands even, and we are not able to make measurements that are so, we say, fine-grained that they're able to resolve and to kind of give us information about the whole dynamics. Instead, we're able to make only these measurements that are kind of blurry. So they only give us very partial information. They're only able to capture that partial information. And the reason that this happens, that these measurements are coarse and they're so blurry, is because actually that information, the information from the initial state, is transferred in the correlations between the parts of the system, and specifically some quantum correlations. So if we think of like a group of atoms or molecules that are all interacting together, then as time goes forwards, like let's say an atom starts forming quantum correlations called entanglement with the other atoms in the system. And the information gets spread and kept in these correlations. So we can think about it with like this analogy. So if we have let's say we have some coins spinning. Now each coin, like if I make it fall, has a 50% chance of showing me heads or showing me tails. So it's kind of random. The outcome is random. But now let's say that I actually I look at these, I try these many times. So and every time I get heads on the first coin, I also get heads on the second one. And similarly, every time I get tails on the first one, I also get tails on the second one. Then we can see that clearly there are some correlations there between the two coins. We cannot see them when we look only at one coin that appears random. So the information is kind of spread out and kept in these correlations. Now, of course, these coins are a classical system, so they cannot really capture, this is just an analogy, and it cannot really capture like entanglement. Entanglement is only a correlation that can happen only in quantum systems, and is actually much stronger than anything that we can have in classical systems. And this leads to actually a crucial difference between classical physics and quantum physics. So in classical physics, if we know perfectly the state of the whole system, then we also know perfectly the state of a subsystem. But in quantum physics, that is not the case anymore. We can know perfectly the state of the whole system and still know nothing about the state of the subsystem. It can be completely random. And that is because this information is all kind of spread in this entanglement. So in classical physics, so this matters for thermal equilibrium, because in classical physics, we often use to justify the emergence of this equilibrium, we have to use some sort of like epistemic ignorance. We have to say, well, the measurements that we can make are always like a bit imprecise. And so when we measure something, we don't really know exactly the value that the system actually has. And so we need to consider kind of an ensemble of values. But in quantum physics, this emergence of thermal equilibrium is much more fundamental, because we have a sort of ontic ignorance about the state of the subsystem, and there's this much stronger quantum correlations, and so yeah, there is we don't need to like kind of mention our the problems with like the epistemic knowledge, like problems with like how we acquire the information, but really it's a fundamental question. So I've talked about like the mechanism to reach thermal equilibrium, and how this takes place. But in fact, we can ask another question. Well, now we know how it happens. Can we actually find ways to make it so that it doesn't happen? And in fact, the answer is yes, we can. Don't want to go too much into the details here, but there are various experiments that you can do, and various particular ways in which you can construct a system so that the system is in some way either resistant or even resistant to thermalization, or even thermalization does not take place. And so just to conclude, I want to mention a few open problems. So firstly, we've made a lot of progress in understanding how this equilibrium emerges, this irreversibility emerges in quantum systems. But we actually still haven't fully understood like the complete set of conditions that leads to this emergence. So we don't have all the necessary and sufficient conditions to explain this emergence. Secondly, and kind of relatedly as well, can we find other ways to break it? And thirdly, can we determine how long it's going to take to reach equilibrium? So it's not only a question of will it eventually reach equilibrium, but also how long will it take to do so? And this is the problem of timescales is actually a particularly interesting problem. We have two main approaches at the moment. And the first approach predicts extremely long timescales compared to what we actually observe experimentally. While the second approach predicts extremely short timescales compared to the experiments, in the vast majority of cases at least. So kind of like Goldilocks, we want to find that just right timescale. And there's a lot of progress that needs to be made on this from a theoretical standpoint. So I just would like to conclude with a quote by Heisenberg. He said it in a different context, but I think it's very fitting here. What we observe is not nature in itself, but nature exposed to our method of questioning. So the reason we see thermal equilibrium is really because of the measurements that we are limited to make. Thank you for listening, and I'm happy to take any questions.